Yours are. It's not broad.
It's chapter 1. Okay, guys. Okay, guys. We're starting into lesson 1.2. The chapter 1 notes are short. I mean, we get some much longer notes later in the year. Okay, so it's just chapter 1. Mrs. Rogers' notes in chapter 1 were probably pretty short too. So, you just don't remember a year ago.
Sort of.
Okay, guys. Lesson 1.2 is we're going to start talking. It's properties of real numbers, and we're going to start by talking about number systems. So, for the last however many years of school, okay, when you talk about numbers, all the numbers we talk about are what we call real numbers. Yes? Everything falls into the real number system. You don't know anything outside of real numbers. Eventually, I can't remember if it's first or in the first semester or second semester. I think it's second semester. We'll learn imaginary numbers. Okay? That's something new we'll do in Algebra 2. But for right now, all you know is real numbers, right? So, this graph here, or this shape here, represents real numbers. And then we're going to look at the different categories of numbers. Okay? Real numbers break into 2 categories. Real numbers can be rational or they are irrational. So I'm going to break up and kind of draw a vertical line here. And to the left, this whole side are rational numbers. To the right, this whole side is irrational numbers. So all real numbers are either rational or irrational. If I give you a real number, it has to be one or the other. Now, what do you remember? Do you remember anything about what a rational number is? Cameron? Okay. Terminating decimal, or there's another type of decimal it could be. Repeating decimal. Okay. A rational number either has a terminating decimal, so a decimal that ends, or a repeating decimal. We also talk about it's a number that can be expressed as a what'd you say? Fraction. Yep. Any number that can be expressed as a fraction. So those decimals that end like 0.5, we know 0.5 is a fraction, right? That's 1/2. Okay. Repeating decimals, those also can be fractions. So rational numbers, and I'm going to put a definition over here. They can be written as a fraction. That's my official definition I like. If you want to put down at the bottom also that they are a repeating or terminating decimal, you can put that as well. And I abbreviated those. I can. Sorry, I didn't realize I was off the screen. Thank you. Nope, just when I go off the screen, you just got to remind me because I'm not always looking at it. Okay, so rational numbers, they can be written as a fraction. They're either a terminating decimal or a repeating decimal. Can you give me some examples of rational numbers? 1. Can 1 be written as a fraction? Yeah. 1/1. 2. Can 2 be written as a fraction? Yeah, 2/1. Okay, change it up on me. Give me something else.
0.75, 329. I like mine.
Okay, I'm going to go with the 0.75 first. How can 0.75 be written as a fraction?
3/4.
It's 3/4, right? Or if you don't know 3/4, it's also 75 hundredths, which can reduce to 3/4. Okay, so it's a terminating decimal there, right? Okay. What about something like 2/3? Is that rational?
Yes.
Yeah. 2/3 is a fraction. Okay. What about 0.3 repeating? No.
Oh, yeah.
0.3 repeating is 1/3, which is why I used it. So 0.3 repeating is 1/3. 2/3 is actually 0.6 repeating. Okay? But 0.3 repeating becomes 1/3. Because the shortcut here is 0.3 repeating. Instead of putting the 3 over 10 and saying 3/10, you put it over 9. Well, what's 3/9? What does 3/9 reduce to be? 1/3. 2/3 is the same thing as 6/9. You put the 6, the 0.6, the 6 is repeating, that's 0.6. Let's see. One other example. Rationals. Do they have to be positive?
No.
No. They can be negative. I'm going to say negative 7.5. Put the decimal in the middle. Does negative 7.5, can I write that as a fraction? Yeah, it's 7.5, right? Which technically could become 15 halves, but it can be a fraction. Okay, so those are all rational examples. They can be written as a fraction. Now, let's go ahead and talk about irrational. So if a number is not rational, it is irrational. What does it mean to be irrational? Okay, a decimal that does not end, so it does not terminate, and does not what else? Repeat. Okay, so you can also say decimals or numbers that cannot be expressed as fractions, but it's sometimes hard to know. So we say decimals that do not end or repeat. I'm going to put that over here. Decimals that do not, will be official, I'll say terminate or repeat. So irrational, decimals that do not terminate or repeat. What's the irrational number that's most common to you guys?
Pi.
Pi. Okay. 3.1415 something something something. We know it goes on and on forever and ever, right? It does not end. It does not repeat. Now, there's another type of irrational number that you guys work with besides just pi. Some square roots are irrational. Now, okay, what if I say the square root of 4? The square root of 4 is 2. So where's that fall? That falls into rational. So I'm going to throw that over here. Oops, I just wrote the wrong thing though, didn't I? My brain said one thing, and I combined it, and what I was trying to say there is square root of 4, because square root of 4 then is 2. 2 over 1 is a fraction. Now, what's the square root of 3?
Some decimal.
Okay, some decimal. Guess what? That decimal is irrational. It goes on forever. It does not end. It does not repeat. Okay, so that's square root of 3. So any of these square roots that are not perfect squares. So square root of 2, square root of 3, square root of 5, square root of 6, square root of 7, square root of 8. I'll skip square root of 9, square root of 10. You see my point?
Yes.
Okay, those are all irrational numbers. If I throw a square root of 7 in there. I don't know, just looking for a random example. Okay, so all real numbers are rational or irrational. If it's irrational, it's just irrational. There's nothing else to go with it. If it's rational, there's some subcategories. First one I'm going to talk about, integers. So some rational numbers are integers. Do you remember what it means to be an integer? Good. Yep. Positive or negative whole numbers. Rather than writing in words, what I like to do is I just like to kind of say, okay, dot, 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 -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. You get the idea then, right? If I list the idea, it's a whole number, which we haven't even talked about what that is, but that means no decimals, no fractions, positive or negative, or 0. Okay? So integers. Now, so there's rational. Some rational numbers are integers. Some integers are whole numbers. What's a whole number? We just use that word. Positive, right? It has to be positive, no fractions, no decimals, and positive or 0. So 0, 1, 2, 3, so on and so forth are my examples for whole numbers. Easier just write the examples and put them in words. Okay? So whole numbers, 0, 1, 2, 3. And then notice I have one more spot to fill in, yes. Some whole numbers are what we call natural numbers. Natural numbers are also sometimes called the counting numbers. So what's the difference between whole and natural then, you think? Zero. When you start counting, what do you start counting at usually? 1. I don't say, okay, there's student 0 and then student 1, 2. No. We start at 1, don't we? And so natural numbers, they just start at 1. So 1, 2, 3, so on and so forth. Okay, so those are kind of your subcategories. Have this list beside you, right? Have this diagram beside you. Be familiar with the words, because sometimes like a word cloud might say, okay, find an integer that meets these requirements, or, so you need to understand what these words mean. I don't think any of them are new to you. It's a reminder. Okay, one way you're going to use this, look at example 1 there. Your school is sponsoring a charity race. Which set of numbers best describes the number of people who participate in the race? So we're picking one of our vocabulary words from above. To this side, it says which set of numbers best describes the number of people who participate in the race. So think about those words there. What's your thought, Jocelyn? Okay, so we have to exclude decimals, right? Because we're not going to have half a person participate. Okay? Can we have negative amount of people participating?
No.
No. So we have to exclude integers. So she took us to natural, which I would agree with. What were you going to say, Cam?
I was going to say whole. What about midgets?
They still count as a whole person. Okay, so, and that's a borderline case, okay? I agree with natural, because I would like to think if they're having this race, there's one or more people participating. However, if this was something like a quiz or a test, I don't think I would count whole wrong. Does that make sense? Anything that includes negatives or decimals, okay, I would count those wrong. But, I'm flexible with that 0. So my answer here is natural. And if you want, you can just write that. If you want an explanation, I'm going to say cannot have negative or fractions of people. Okay, so if you want to write something down to remind you why you picked natural later, or why we as a class picked natural, there's something to write down. Okay. If each participant made a $15.50 donation to a local charity, Which set of numbers best describes the amount of money raised? So each participant donated $15.50. What set of numbers could we use here to talk about this?
Rational.
What do you say, Justin?
Rational.
Rational? Why rational?
Because 1550 is
Okay, we have to have a decimal in there, don't we? And so to talk decimals, we either have to go up to rational or irrational. Well, 1550, it terminates, yes? And even if you add more 1550s, it's still going to terminate somehow or another, isn't it? It's either going to end in 0 or it's going to end in 50. So I would agree with rational numbers. And that's because we need the decimals. I'm going to say need to include, and I'm going to say terminating decimals. Okay. Moving along. Example 2. Example 2 says, plot the numbers, -5 halves, square root of 2, 2.6 repeating on a number line. Okay, so, first of all, I'm going to label my number line. And I think as long as you go as low as -3 and as high as +3, you'll be good here. So I'm going to put tick marks at each spot and label my numbers. -3, -2, -1, 0, 1, 2, 3. Now, my suggestion is, can we think this through without grabbing the calculators and plugging stuff into the calculators? And some of you may have already plugged stuff into the calculators, that's fine, but how do we process this without just automatically picking up the calculator is what I'm asking. You see what I'm saying there? I know, the calculator's there, you want to just put it in the calculator, forget what it is, but we can do this. -5 halves. You have to divide it, right?
yes.
Think with me. 2 goes into 5 how many times? 2 times. With a remainder of what? 1 over the original denominator of 2. Does that sound familiar?
Yes.
And I'm not saying you have to write it out. You can think through this in your head, right? 2 divides into 5 2 times. 2 times 2 is 4. Remainder 1. And so then it's 2 and 1/2. So 2 and 1/2 is the same as the decimal -2.5. Okay. Where do we graph -2.5?
In between -3 and
Yeah. In between -2 and -3.
2.
I'm going to put a dot there, and I'm going to label that as -5 halves. Okay? Again, I'm going to ask you to think about this without a calculator. Square root of 2. Come up with what numbers does it have to be more than and less than? Okay? Has to be less than 2. And here's the deal. Think about perfect squares. Above the square root of 2, we know the square root of 4 is 2, right? So it has to be less than 2. Below the square root of 2, what's the square root of 1? 1. So what I'm saying here is that somewhere it's between square root of 1 and 4, isn't it? So it's between 1 and 2. Now, does that give you enough information to graph it? Somewhat. I mean, if we're estimating. Which one's this going to be closer to? 2 is closer to 1 than it was 4, so it's going to be closer to 1. And, can you put it in the calculator and check yourself? You can. The calculator is going to tell you 1.414. I don't know after that, but the point is be able to estimate it also. So if square root of 2 is 1.414 something, where do we graph that?
Closer to 1.
In between 1 and 2, slightly closer to 1. And 2.6 repeating? In between 2 and 3, closer to 3 than to 2. Okay.
How can you graph the repeating decimal?
How can I graph what?
The repeating decimal.
Well, it still fits there somewhere. I mean, obviously that's not, incredibly precise, It's just in the area of 2.6, 2.7, so. Okay, example 3. Again, I'm going to suggest we don't pick up the calculators yet. Okay? It's not that you can't check yourself, but how do square root of 17 and 3.8 compare? So just thinking about the square root of 17. I don't know this one off the top of my head, but I can tell you what whole number it's closest to. Can we agree there? What do we know about the square root of 17? It's close to what? The square root of 16. And why is the square root of 16 important? Because we know it, right? We know the square root of 16 is 4. We also know, if I say, can you agree the square root of 16 is less than the square root of 17? 16 is smaller than 17, so the square root of 16 is smaller than the square root of 17, which means the square root of 16 is 4, the square root of 17 is bigger than 4, isn't it? Okay, which means it's going to be 4 point something. Now, we're trying to compare this to 3.8. What do you know about 3.8? We know that 3.8 is smaller than 4, isn't it? So if 3.8 is smaller than 4, and the square root of 17 is bigger than 4, what can we say? Yeah. You can say, and I can accept it either way, 3.8 is less than the square root of 17, or you can say the square root of 17 is greater than 3.8. What I will say, I'm trying to remember how Math Excel sets it up, and I don't think you get to pick which way you put the numbers in. So they'll have the numbers in, and you have to put the sign in. So you'll just have to pay attention to which one's bigger. But that's reasonable to do without a calculator, isn't it? I know it's going to start 4 something. Probably 4.0 something or 4.1 something. It's not going to go very far. Okay? But it's enough to be bigger than 3.8. Okay? Can you use the same idea for this next one? What do you know about the square root of 26 and 6.25? Square root of 26, what comes to mind? Square root of 26 is close to what? Square root of 25? So if we use that, and that's the common one, right? We know the square root of 26 has to, excuse me. Just totally goofed this. Okay, what that's supposed to say, can you guys read that? Square root of 25 is less than the square root of 26. Because 25 is smaller than 26, right? So that's saying that 5 is smaller than the square root of 26. Okay. Now, what do we know about 6.25? Okay. So look at the situation we ended up with here. Square root of 26 is bigger than 5, and 6.25 is bigger than 5. Did that help us any? Nah, not exactly, did it? I mean, we're close, but here's the deal. I do it too. Square root of 25 is closest to square root of 26, isn't it? So that's what we went with. Well, we need to know what's on the other side. Square root of 25 is what's smaller than square root of 26? What's bigger than square root of 26? That we know. And that's what? Square root of 36? So what you can think about here instead is, okay, let's reverse this. Square root of 26 is smaller than the square root of 36. So that means the square root of 26 is smaller than 6. Okay? Now, how does 6 compare to 6.25 though? Does this help us? Square root of 26 is smaller than 6, but 6.25 is bigger than 6. So now can you make that comparison? Yeah, what do we know? Square root of 26 is smaller or less than 6.25. And if you'd prefer to reverse that the other way, I don't have a preference. As I said, I can't remember exactly what Math Excel expects you to do, but okay. One more topic. We're going to kind of squeeze things in carefully, I think. Barely. Number properties. You'll be asked to use some of these names here, so you kind of need to have an idea of what property is which. Now, you've been working with a lot. These are not new properties to you. Commutative property, associative property. My kids learn those in elementary. Okay? You relearn them every year. I've already taught them in pre-calc and calc this year, I think. Or I shouldn't say taught them, I've reviewed them. So that's what we're doing here. Now, the closure property, okay, you might not be familiar with that one, but that's just saying if you add two numbers, A and B is a real number, or if A and B are real numbers and you add them, you're still going to get a real number. If A and B are real numbers and you multiply them, you're still going to get a real number. That's all it's saying there. Okay, commutative. A plus B equals B plus A. That's saying, okay, if I say 2 plus 3, what do you know about 3 plus 2? It's the same, right? It doesn't matter which order I add. Same thing if we multiply. And notice that's a commutative property of addition or commutative property of multiplication. You have to be able to also identify addition or multiplication. Okay, associative. I like to think of the associative. It has 3 pieces. Those 3 pieces stay in the same order, but the parentheses move. And so here, A plus B plus C is equal to A plus B plus C. The difference is here, parentheses are around the second and third piece. Here, parentheses around first and second piece. Also works with multiplication. A times B times C, A times B times C. The grouping symbol, so the parentheses moved. In this case, from second and third to first and second. So this grouping symbols move from beginning to end or end to begin. That's your associative property. Identity property. How do you get something to stay the same? So what can I add to a number that allows it to stay the same? And that's 0. So the adding identity is 0, because if I add 0, something stays the same. What can I multiply something by to get to stay the same? 1. So my multiplying identity is 1. Now the inverse properties are how do I get the identities? So how do I add something and get the identity of 0? And that's when you add a number and its opposite, or a number and its negative. How do I multiply 2 numbers and get the inverse of 1, or the identity of 1? And that's when you multiply, it says A times 1 over A. Think of a number times its reciprocal. Do you guys know what I mean when I say reciprocal? Reciprocal is when you take a fraction and flip it upside down, right? Okay, so that's how you multiply to get 1. And then distributive property, there's not really addition or multiplication here. You guys know the distributive property, right? When you solve equations, A times B plus C means you do A times B plus A times C. Yep, and guess what? You're going to use it a lot this year too. It's not going away. So, okay, flip to the back side. It says state the property each equation illustrates. Two-thirds times 3/2 equal 1. 2 pieces are multiplying to equal 1. What property says that? Not identity. Inverse. Identity, you would multiply something by 1 to get that other number. Here, you're multiplying 2 numbers to get 1. So this is the inverse property. And officially, it's the inverse property of, is this addition or multiplication? Multiplication. Had I thought about it sooner, they might call it the multiplicative inverse. Just putting, they might call it the multiplicative inverse. I don't remember their wording. Okay, what about B? 3 times 4 and then times 5 is equal to 3 times the quantity of 4 times 5. 3 pieces in the same order. They stayed in the same order, parentheses moved. So this is the associative property of multiplication. Okay. Look carefully at C. What changes between the left side and the right side? Okay. She says they put the 3 in the parentheses. So did the 2G change? So here's what I would suggest. Kind of block out the 2G's. Does that help if you block out the 2G's? The 2G's didn't change. They didn't move. They didn't change. So don't think about 2G's. Just think about, okay, what's happening with the rest of it? So if I ignore the 2G's, you can see that 3 times G and 3 times H, can't you? So that is the distributive property. And there's no, it's not addition or multiplication, it's just the distributive property. And lastly, 5x plus 0 still equals 5x. Identity, how do you get it to stay the same? And this is the identity property of addition. Okay, guys, your homework is in Math Excel. It is called Lesson 1.2. I'm not very creative with the names here. I keep it so you know what it is. So it's Lesson 1.2. It's in Math Excel. It should be available as of this moment because I would have made it come available sometime during this class. And it will be due tomorrow. Okay? It'll be due tomorrow during this class. So again, work on it, and then come back with any questions you might have. You're also always welcome to stop me before school, after school, homeroom, those type of places, and ask questions as well.